Hello students, welcome to today's session on Kepler's law from the unit Gravitation. Okay, so Kepler's this particular segment is a very important unit in this discussion. So Kepler has basically deduced certain laws which are describing as the planetary motion. Okay, so let's move to the first law. All planets which are moving around the sun in elliptical orbits have the sun at one focus of the orbit, which means that the central point, is none other than our sun. About which the planets rotate. Okay, so if this is the sun, these are certain circular orbits along which the planets will cause its rotation, and they will all revolve around this particular sun. So if this is Mercury, this is Venus, we can all find that stars and even the planets are all revolving around sun. So that's the first law, which is also known as the law of orbits, because orbits are specific paths along which the planets rotate. And yeah, and they all rotate and they do not they don't break their paths. Yeah. Second law is the law of areas. A line which is joining any planet to the sun, line which is joining any planet to the sun is sweeping out equal areas in equal time intervals. It only means that in this diagram we can see the equal amount of area which can be swept across. So if a planet is a revolving sun, it is sweeping equal areas, as we can see dA, in equal time interval dt. Okay, that is the smallest time interval possible. That is, the aerial speed of the planet remains constant. The aerial speed never changes. It remains to be as a constant. Okay. According to this law, the planet which is nearest to the sun and then its speed is maximum. If the planet is nearest to the sun, the speed delivers out to be maximum. And when it is farthest from the sun, its speed is minimum. Okay. Its speed is minimum when it is farthest from the sun. If you have the maximum amount of distance from the sun, the speed is minimum. In figure, if a planet moves from A to B, that means this position to this position. If this is the area which has been swept by the planet from A to B in a given time interval, and from C to D in the same time interval, the areas ASB and CSD. That means these two areas, ASB and CSD, that means S being the central point of their rotation, that is sun, are all coming out to be equal. Now that's a fact. Okay, so this is a law of areas. Okay, dA is equals to the area of the curved triangles. These triangles are not straight, they are curved because one of the edges are curved. Okay, so area of triangles SAB is equals to half times of AB into SA. That means half of base into height. And that's how we are getting RD theta into R, because those were the specific variables which we have taken for the calculation. When we are calculating the instantaneous aerial speed of the planet, this is dA by dt, which is equals to half R square d theta by dt. And from here, we can get half times R square omega, which is the first law, where omega is the angular speed of the planet. Omega turns out to be the angular speed of the planet. It is a d theta by dt, basically the motion which is possessed by that particular object in unit time interval. Let J be the angular momentum of the planet about the sun, S and M be the mass of the planet. J is equals to I times omega. Okay. These are the certain laws we are causing the derivation, and J is the angular momentum. So angular momentum is turning out to be moment of inertia into the angular velocity, which is mr square times omega, because that's what a sphere possesses. That's what has been written. And then these two equations, when we are equating from these two equations, we can frame out the value of dA by dt, which turns out to be J by 2m. Yes, that's the third equation. And now the aerial speed, dA by dt, that means the differential of this is a constant. And according to Kepler's second law too, so theoretically and mathematically, both we have this, that dA by dt is always a constant. The area swept across unit time interval is a constant. Okay. Now, this is one of the most important points which we can note. That angular momentum of the planet is constant and angular momentum of the planet is conserved. Yes. So it is equivalent to the conservation of angular momentum. The third law. Square of the period of revolution. That means the revolution which we are, the revolution in unit time which is occurring, the square of it is directly proportional to the cube of the major axis and minor axis. Now, there are two axes of the elliptical path. The greater area which is getting covered by the axis is known as the major axis, and the smaller area which is getting covered is the minor axis. So, if A and B are the semi-major and the semi-minor axes of the ellipse, then the area of the ellipse will be pi times AB, because that is the area of ellipse. Hence, if t is the time period of revolution, we get it as to be time period is equals to area of ellipse upon the aerial speed. We are substituting the area as the numerator and the denominator to be the aerial speed, and hence calculating t square is equals to 4 pi square m square a square b square upon j square. That's it. And let L be the semi-latest rectum of this. This is not relevant actually for the CBSE boards. But yes, if L is equals to B square by A, this is a specific stimulation which we get it in maths. Then T square is equals to 4 pi square M square A cube L upon J cube. Where we can also say that the square of the time period is directly proportional to the cube of the area swept. As all the other quantities are constants, it's very clear that the farthest planet will have the largest period of revolution. You can consider the period of revolution of Uranus and Neptune to be much greater than what it could be for Mercury, which is a henceforth absolute, because it cannot be the same. As the radius is more, the diameter is more, and Uranus and Neptune are sweeping greater areas around our sun. Let's consider one of the questions. It's an NCRT question to 8.23. A star 2.5 times the mass of the sun collapsed to a size of 12 kilometer. It rotates with a speed of 1.2 revolution per second. Extremely compact stars of this kind are known as neutron stars. Certain stellar objects called pulsars belong to this category. Now, this is an extra knowledge which has been posed to us by the examiner. Will an object placed on its equator remains? Now, this is a very hypothetical and fictitious kind of a question, as we are dealing with this. Okay, will an object placed on its equator remain stuck to its surface due to gravity? Now, candidates in examination will find it difficult to cause the mathematics of it. So each and every NCRT question is very relevant, student, and you must practice everything. Yes. So the mass is 2.5 times 2 into 10 raised to power 30 kg. It turns out to be 5 into 10 raised to power 30 kgs. And what is the radius of the star? Which is capital R. It is 12 kilometer And in SI, we can say 12 into 10 raised to power 3 meters. So the gravitational force is G mm upon R square. All will be part of my derivation. All will be part of the classes into which these derivations will be dealt. This turns out to be the constant value. In many exams, you can find it. To be given up by the examiner. Fg is equals to 6.67. Mass we don't know. Substituted by the radius divided by square. That's it. And then calculating it, must receive 2.37 or 31 into 10 raised to power 12 Newton. Mass times Newton. Mass, we don't know what's the mass. Now we need to calculate the centrifugal force, which is also known as the pseudo force. Centrifugal force is the second step, which we'll be calculating, and it is a pseudo force. It's applied only when you have an external force which is getting applied. To calculate it, we must know the angular speed, which will turn out to be in omega. Omega will be 2 pi times the revolution which is causing 1.2, turning out to be 7.54 radian per second. Yes. Now what will be the centrifugal force? I'm denoting it to be the centrifugal force, Fc. The formula which was seen in our above mentioned derivation when I was explaining m omega square r. Now you see, substituting m into 7.54 and the square of it times radius 12 into 10 raised to power 3. Calculating it, you will be getting 7.5 square. Okay, which could be like it's 756, 5625 under those measures, and then multiplying it by 12, not 6 but 12. It will result out to be 6.82 into 10 raised to power 5 meter Newton. Students need to practice the mathematical part of it till grade 10. Your mathematics should be good. Your basics should be good. Because that's expected from a grade 11 candidate. Fg is 2.31 into 10 raised to power 12 meter Newton. And then we have Fc to be 6.82 into 10 raised to power 5 mass Newton. So mass Newton. Yes. So what could be done? As we all know that the gravitational force, we'll be writing it with some other color pen. Gravitational force is much, much greater than the centrifugal force. Okay. So the inward gravitational force is significantly greater. then the centrifugal force. So the object placed on the equator will stick. Examiners even check the final answer statement which we write, just the way we used to write in grade 10. So the object which is placed on the equator of the neutron star will remain stuck. That's it. Rest is understood. So yeah, students, this marks the end of this session. And keep practicing, students. I'll be seeing you in my next classes. Till then, if you have any doubts, please revert to my Urban Pro profile. Thank you so much.